Hello students, today we are going to discuss about an important topic in electrostatics, which is electric field. Electric field due to a charged circular arc. Electric field due to a charged circular arc. Okay, so let us suppose this is a positively charged circular arc. It is a positively charged, having positive charge, positively charged circular arc. Our aim is to calculate electric field with respect to this positively charged circular arc at a point O. This is the point O. So our aim is to calculate electric field with respect to the circular arc at a point O. So initially, the direction of electric field, because this is positively charged circular arc, this is the direction of the electric field, and the two portions divided with equal angles. Here this is theta by 2. Let us suppose the angle is theta by 2, and this is also the angle is theta by 2. With equal angles it will be divided. So this is a continuous charge distribution. So before going to solve any problem related to continuous charge distributions, initially we take a small portion of the circular arc here. Initially we take a small portion in the circular arc. With respect to the small portion, we calculate the small electric field, and after that we integrate to the limits. Here whatever the limits existed, we integrate for those limits, then it will give the final result. Okay, let us suppose a small element here. This is a small element having length dx. Dx is the length of the element on the circular arc, and that small element having the charge dq. dq is the element having the charge, small element having charge. And next, this small element makes an angle. The small element makes an angle d phi at center. The small element make an angle d phi at center, and this is the radius r of the circular arc, and the small element from the center line, dotted line, the small element, the angle phi. The small element is at an angle phi with respect to the center line we drawn. And next, actually the element having the electric field, this is the direction of electric field with respect to the element we can take. See, this is the small element. With respect to the small element, the direction of the small electric field, because this is positive charge, electric field direction away from the positive charge. So at center O, this is the direction of the electric field, and this electric field here, phi is the angle, and if you extend the dotted line here, if you extend this dotted line, this angle is also phi, right? Here we take, this is the angle phi, here also this is the same angle phi. So that electric field is divided into two components. The small electric field is divided into two components. One is dE cos phi and another one is dE sin phi. So dE cos phi and dE sin phi. So this dE sin phi components are cancelled, because if you choose the same element on the other side here, we get the dE sin phi component on the opposite direction also. So dE sin phi components have the possibility equal and opposite. So the dE sin phi component, due to the symmetry, it will be cancelled. So dE cos phi component is the resultant electric field here. Okay, so dE cos phi is the resultant electric field here. So the resultant electric field is equal to dE cos phi. Resultant electric field is, so the total electric field we can integrate on the both sides. So ER is equal to integral of dE cos phi. We substitute the value of dE there. dE means small electric field with respect to the small charge dq. It makes distance from dq, from dx to center O, the distance is r, so that k into dq by r square is dE. Okay, so k into dq by r square, because dq is the small charge of the small element we choose, and here this is the distance between the small element to the center O is r, so that k into dq by r square is the element dE. So we substitute the same there, k into dq by r square into cos phi. Okay, next dq in terms of charge density, we convert in terms of charge density the value of dq. Charge density means let lambda is linear charge density. Let us suppose lambda is the linear charge density, then dq is equal to lambda into dx, right? Because the dx length having the charge dq, so charge per unit length is lambda, so charge per dx length is lambda into dx, that is nothing but dq, right? So in place of dq lambda into dx. And again one more point, dx is the arc length, d phi is the angle here, so angle is equal to, we know, arc by radius, so that arc length is equal to r d phi. So in place of dx we substitute here r into d phi. So finally dq is equal to lambda into r into d phi. So substitute in the above equation, resultant electric field is equal to integral of k into dq means lambda r d phi by r square into cos phi. Okay, so here r cancel, and k into lambda by r integral of cos phi d phi. That is the final expression. Next, cos phi integration and then limits. What are the limits here? Here the limits is, initially we take the half portion is theta by 2, clockwise half portion is theta by 2, anti-clockwise half portion is theta by 2. In anti-clockwise direction generally we take minus angles, so that minus theta by 2 2 theta by 2 is the limits, integration limits. So integration limits are minus theta by 2 to theta by 2. So electric field is equal to k lambda by r into integral of cos phi is nothing but sin phi. So that sin phi, the limits are minus theta by 2 to plus theta by 2. So if you substitute, resultant electric field is equal to k lambda by r into sin theta by 2 minus of minus sin theta by 2. So that the resultant electric field term is 2k lambda by r into sin theta by 2. This is the resultant electric field due to the charged circular arc. Okay. So again, the steps I again explain to you. The first step is, initially our aim is to calculate the electric field due to the charged circular arc, and this charged circular arc, a small portion we consider, because this is continuous charge distribution. We take a small portion, and this small portion made an angle phi with respect to the line, dotted line we drawn here. So that this is the angle phi, and the dotted line above the angle is theta by 2, below the angle is also theta by 2, and r is the radius of the circular path. Then this is the dq is the small elemental charge. Lambda is a linear charge density, so that dq is equal to lambda into dx. So initially we calculate the small electric field with respect to the small element dx. It is dE cos phi. dE sin phi components are cancelled due to the symmetry, and finally the dE cos phi components are integrated with respect to the limits here, minus theta by 2 to theta by 2. Finally we get the result, ER is equal to 2k lambda by r into sin theta by 2. Okay, and this is very important point. In any continuous charge distribution, initially we take a small portion on it, and then finally with respect to the small portion we calculate the component of field, and finally we applied the limits to that component by integration. Okay students, let us discuss the various cases in it. We get the resultant electric field is 2k lambda by r into sin theta by 2. This is the resultant electric field we get. So suppose for a quadrant, suppose if you take a quadrant, an arc made an angle pi by 2 at center is nothing but quadrant. This is the angle theta is nothing but pi by 2. This is positively charged arc, and this is the direction of electric field. So positively charged arc, suppose if you want to calculate the electric field with respect to this positively charged arc, which makes an angle pi by 2 angle at center. In this case, directly we substitute in this formula, you get the result. Let us suppose ER is equal to 2k lambda by r. R is the radius of circular path, lambda is the linear charge density, and theta, in place of theta, pi by 2. So theta, sin theta by 2 formula. So theta by 2 means pi by 2 by 2, that is pi by 4. So the resultant electric field is equal to 2k lambda by root 2 r, which is equal to ER is equal to root 2 k lambda by r. This is the resultant electric field with respect to an arc made an angle and a quadrant which is made an angle pi by 2 at center. So if it is arc made an angle pi by 2 at center, this is the result root 2 k lambda by r, because sin pi by 4 is equal to 1 by root 2, right? This is case 1. Next, suppose semicircular arc. If it is semicircular arc in this way, semicircular arc, then this is the direction of electric field. If it is negative charge, the electric field is upwards, the electric field is downwards, because that is positive charge. So semicircular arc, in that case the theta is nothing but pi, right? It made an angle pi at center. So that semicircular arc is given in the problem. Immediately substitute pi in place of theta. Then we know the relation ER is equal to 2k lambda by r into sin theta by 2. Sin theta by 2 is nothing but here pi by 2. Sin pi by 2 value we know it is 1. So resultant electric field at point O at center is nothing but 2k lambda by r. So if you know the linear charge density and radius, it is possible to calculate the electric field in these two cases. And next, case 3. If suppose circular arc, it's like a circle, semicircle, here this is circle, a complete circle having positive charge. Let us suppose in this case we know circle made an angle 2 pi at center, so theta is nothing but 2 pi. So electric field ER is equal to 2k lambda by r into sin theta by 2. That is sin theta means theta is 2 pi, 2 pi by 2. 2 pi by 2 is nothing but sin pi. Sin pi is 0. So resultant electric field at center is 0 with respect to circular charged arc. Okay. Let us discuss few problems related to this concept. The example 1 is given. Half of the semicircle, here the semicircular arc is given, but half of the semicircular arc having positive charge, half of the semicircular arc having negative charge. Then what is the electric field at point O, center of the semicircular arc with respect to that charges? So that initially in which direction the electric field is located with respect to the given semicircular charged arc. See that this is positively charged. If you draw a dotted line, positively charged quadrant, if you take, this is the quadrant positively charged, and this is the direction of electric field. This is the direction of electric field with respect to the positively charged quadrant, right? And this is negatively charged quadrant, and this is the direction of electric field E with respect to the negatively charged quadrant. And because the electric field direction is from positive to negative, so that electric field is towards negative in case of a negatively charged quadrant and away from the positive in case of positively charged quadrant. And the angle is 45 degrees because this is semicircular. Here the angle is 45 degrees. So what is the resultant electric field? Here the resultant electric field is the component of these two electric fields will give the resultant electric field. Suppose if you draw separately those components, this is E and this is also E. Suppose this is Y direction and this is X direction. It is the angle 45 degrees and it is also 45 degrees, right? So if you take the component of the electric field E in upward direction, this is E sin 45. Here also in downward direction, E sin 45 due to these two electric fields. In X direction, E cos 45 plus E cos 45. In X direction, the components of these two electric fields. And if you notice, these two electric field E sin 45 components are cancelled due to the symmetry here. So that E sin 45 is cancelled and E cos 45 components are added. So the total electric field, resultant electric field is the sum of E cos 45 plus E cos 45, which is equal to 2E cos 45. And next, what is E? With respect to the semicircular arc, we calculated already the electric field due to the semicircular arc in case 1, that is 2 into root 2 into k lambda by r. Actually electric field with respect to quadrant, here positive is quadrant, negative is quadrant. So with respect to the quadrant, we take electric field E. Here also electric field E with respect to the quadrant. So the electric field with respect to quadrant of the arc is equal to root 2 k lambda by r into cos 45 is root 2. So finally 2 k lambda by r, which is the resultant electric field along the direction of x. So that 2 k lambda by r into I cap is the result of the given problem. Okay students, so here the problem, the semicircular arc is divided into two quadrants, so that the two quadrants having two different charges. So the electric field directions are different because of the two different charges. Finally we calculate the resultant electric field by the known relation. And next we will go to the example 2. See, find electric field at O. Similarly, whatever we solve here, the same problem there, but here and there is a different. Here this is quadrant and there it is semicircular. See, here the positive portion is semicircular, negative portion is also semicircular. So the electric field due to the positive portion is along the direction E. Electric field due to the negative portion is also along the same direction E. So the resultant electric field in this case is E plus E, that is 2E. 2E is the resultant electric field in that case, and E is the electric field due to a semicircular arc, charged arc. Already we calculated the electric field due to the semicircular charged arc is 2k lambda by r in case 2. So that what is the resultant electric field? 2 into 2k lambda by r, that is 4k lambda by r. If it is taken as x direction and this is y direction, so 4k lambda by r into I cap, this is electric field. Okay, because the circle having not a similar charge, circle having different charge, half of the portion of the circle having positive charge and half having the negative charge. So that electric field at center is 2E. If it is having the same charge, already we discussed the case 3 in the previous topic, in the previous cases, so that in that case 0. But here the total circle is divided into two semicircular arcs, so that having different charges, and positive charge the electric field is outwards, negative charge is inwards. So the resultant electric field at center is 2E, and E is the electric field due to a semicircular charged wire. Okay, so E already 2k lambda by R, we know the relation. Finally, the resultant electric field at center with respect to the given problem is 4k lambda by R. The direction is into I cap along the x direction. Okay students, this is the topic today, and it is very important topic in electricity. So I hope you understand the topic what we are discussing today, and we will continue the electrostatics in the next video.